Hello, welcome to your video on compound events in probability. In this video, we'll kind of half recap things we've seen, but also take important steps forward. Let's begin. To begin, we have compound events. These are events that are made up of two or more events happening at once or one after another. Just so you know, there is a notes page you can print to go with this video. Okay, so this is important here. If compound events are made up of two or more events happening at once or one after another. In probability, in many ways, there's no distinction between, let's say there was an example we had recently. You reach into a bag, you pull out two marbles. And it's, I think in the example we did, it had the word simultaneously there. In probability, there really is no distinction between simultaneously or one after another really quickly, like a split second between. So you can either reach in the bag and grab two marbles at once, or you can reach in, grab one, and then really quickly grab another. In probability, everything works out the same, whether you think of it as one happening after another. All right, so compound events can be made up of independent or dependent events, which we've seen before. Okay, to recap, independent events are events where the outcome of one event does not affect the possible outcome of the other. For example, when we flip a coin, let's say we were going to flip a coin twice. Your first flip, probability is 50-50. Then you flip again. The probability is still 50-50. The results, whether you got a head or tail on the first flip, has no impact on the probability of the second flip. Those are independent events. For independent events, when we want to find the probability of one thing and the next one happening right after, or if you want to find out the probability of both happening simultaneously, all we do is multiply the two probabilities. If you have more than two events making up the compound event, you just multiply all those probabilities. Okay, dependent events. Events where the outcome of one event does affect the possible outcome of the other. These are also called conditional. These are found the same way as independent events. An example of dependent events would be, let's say I check the weather, and it is a small chance it's going to be really cold and a big chance it's going to be warm. Okay, so that probability of, or the outcome of whether it's warm or cold outside will determine whether I wear a hat out. So the outcome of what kind of weather is it determines the probability that I will wear a warm hat or not. So now these events are dependent. My choice of hat depends on what happened with the weather. So for dependent events, the formula is the same. You still multiply the two probabilities. And please don't be confused by the symbol. Imagine it the same way as the last problem. All you do is multiply one probability by the next, and you get your full probability for the dependent event. However, this symbol here tells us that the probability of the second thing depends on what happened in the first one. So again, this probability for the second event can change depending on what happened. So with my example, if it was sunny, then the probability I would wear a hat changes compared to if it's cold, then my probability of wearing a hat is different than otherwise. So that's what that means. It means B, the probability of B, given that A has occurred. So again, A happens or doesn't happen, it changes the probabilities here. Okay, so looking at an example of that, please read this and answer questions A and B. All right, hopefully you noticed the key phrase here that says when after you take the pen out of the pencil case, you put it back. So by putting it back, you are resetting the pencil case. So now everything that happens in the future has the same probability as the first time. These are independent events. So the probability of finding blue, getting a blue than a red pen is just probability of blue times probability of red, and those numbers are 5 out of 7 blue times 2 out of 7 red. And again, it's 7 because you have put the pen back the first time, so the pencil case is exactly as it was in the beginning. There's our answer. Please read this now and try this question, both of them. For this one, notice you do not put the pen back. So now the pencil case changes. So your probability for the second taking of a pen has changed based on the outcome of the first action. These are dependent events. So probability of drawing a blue than a red is found using the dependent formula, which is the same again. You do probability of blue times probability of red except for the probability of red has changed because B has occurred. So probability of blue is the same in the beginning, 5 out of 7 pens, but then you multiply by 2 out of 6 because there's one fewer pen in the bag, and you still have 2, but it's 2 out of 6. All right, let's take a look at some diagrams. This is the key part of what we're looking at today. We are going to talk about diagrams for compound events. Let's say we have a compound event made of two small events. Classic example, flipping a coin. So here, this is called a sample space diagram, and we can say, here's the outcome of coin 1, here's the outcome of coin 2. And again, in probability, it doesn't matter whether you flip the coins at the same time, or one after another, or one and then an hour later another one. The results in terms of how we calculate things are the same. So let's pretend we flip the coins at the same time. On coin 1, we have head, tail, here we have head, tail. Here's all our possibilities that we got a head, head, or head on one, tail on the other, or tail, tail, or tail, head. So there's 4 possible outcomes from flipping 2 coins. We've looked at these in another way as well, and that's a tree diagram. This was a sample space diagram. This is a tree diagram. This shows the same thing. First coin, head or tails. Second coin, head, tails. Second coin here, also head, tails. So whether you get heads here, you have 2 possibilities there. Whether you get tails here, 2 possibilities. In the end, there's 4 paths. There's the head-head path, head-tail, tail-head, tail-tail, and the same thing is shown here. So both of these diagrams show the same thing. A really important thing to notice is that the sample space diagram can only have 2 axes, right? It's 2-dimensional, here and here. That means 2 small events have happened, one coin flip and another, and it shows it here. First coin flip, second coin flip. This sample space diagram is limited. It can only show a compound event made of 2 events. Okay, let's do rolling of dice. So here we have a sample space diagram for the rolls of 2 dice. So here's 1 to 6 on one die, 1 to 6 on another, and here you can see all the rolls. We've talked about this before in our horse race game. So here we have a 1 and a 1 rolled, here we have a 1 and a 2, and so on and so on. Here's a 6 and a 6 rolled. When we looked at this in class though, we didn't have it listed with all the possibilities. We had it like this. We had the sum of all these. So a 1 and a 1 makes a 2, or for example, a 6 and a 6 makes a 12. So here's all the sums. But in the end, it's showing you the same thing. It's showing you all the possible outcomes. So there are 36 possible outcomes, and here's 36 possible outcomes as well. So that's the full sample space, 36 outcomes, and this is a sample space diagram. This could also be shown on a tree diagram, right? Here we go. First die is rolled, 6 possibilities. Second die is rolled, 6 possibilities. So we see 6 possibilities come from each of those. And then if you follow each path, you can see 36 final possibilities, 36 paths that are possible here. For example, we roll a 4 and a 6, and that gives us a sum of 10. And that's the same thing as looking here at 4, 6, and that is a sum of 10. Which one's more convenient? I'd say in this case, sample space diagram. And again, since we have a sample space diagram, only 2 events happened, one roll and another roll. If we did a third die roll, we could not show it on a sample space diagram. Or I guess we could show it in 3 dimensions. But a tree diagram can go forever. So here is a compound event made of 3 or more events. And again, we can see now a tree diagram works. We have a side dish. First, okay, so you're in a cafeteria. You're choosing a side dish, soup, fruit cup, quesadilla, and then a main dish, chicken, beef, fish, or lamb. All right, so all those you see growing from each choice. And then you're choosing a dessert. So third choice, 1, 2, 3 events. Okay, could this be shown in a sample space diagram? Let's try. Here is our side dish, soup, fruit cup, quesadilla, like as we have here. Here's our main dish, chicken, beef, fish, lamb, chicken, beef, fish, lamb. And we have all the possibilities, right? Soup plus chicken, soup plus beef, soup plus fish. So we have soup plus chicken, soup plus beef. But where's the dessert? There is no dessert. We can't show it on here because that is a third action and you only have 2 axes here, 2 dimensions. You can't do anything else. So sample space diagram, no good. But tree diagram, you can keep growing that tree. Okay, let's try a problem here. How many possible outcomes, or let's list all the possible outcomes of the coin flip, double coin flip. We have these possibilities. So how many outcomes are there? How big is our sample space? 4. What is the probability of getting 1 head only? Well, hopefully you figured out 1 head only is this one and this one. Therefore, 2 out of the 4 possibilities are 1 head only. All right, next question. What's the probability of getting at least one tail? Okay, at least one tail means this one, and this one, because at least one means one tail or more, so two tails is okay. So now we have 3 out of 4, 0.75. Okay, let's look at a different example. Here we have 3 coin tosses, so not 2, but 3. So first coin toss, second, third. This one could not be shown in a sample space diagram because 3 sub-events took place here, but a tree diagram works. Notice the probabilities are given, half, 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 and so on. So how many possible outcomes are there in this scenario? What is the size of this sample space? Hopefully you said 8, because the sample space is all the possible outcomes, and all the possible outcomes are how many paths are there in total? And there's 8 different paths. There's the 3 heads path, and then head, head, tail path, and so on. There's 8 possibilities. So what is the probability of getting one head only? One head only is this path, for example, head, tail, tail, or tail, head, tail. That leads to one head only right here. Or tail, tail, head. That also leads to one head. So there are 3 possibilities. This one, which has one head, this one, which has one head, and this one, which has one head. So 3 out of the 8 paths lead to one head only. So there's our probability of getting one head only. It's really important to note right now that this only works, we can only do this method of looking at 3 out of 8 paths because all these probabilities are identical. If these probabilities were not the same, then we couldn't just count the number of paths. To find the probability, you may remember you would have to then find the probability along each path by multiplying the numbers and then adding the probabilities of the paths you're looking at. But we're doing a simple example where all the probabilities are the same, so we can just say 3 paths out of 8. So now try that for the probability of getting 2 heads. Oh, let me go back to something here. For the 3 paths only, okay, sorry, yeah. So for the one head only path, let's follow one of those paths. If you did take the approach of multiplying along the path, you would do 0.5 times 0.5 times 0.5. So those 3 multiplied will give you the probability of that one path. And that is 1/8. So the probability of that one path is 1/8. But since all the probabilities are the same, all the paths will have that same multiplication, 0.5, 0.5, 0.5. So all the paths have a 1/8 probability. So basically, since these are all the same, it tells us each of these outcomes has the same probability of 1/8, 1/8, 1/8, 1/8. So they're all equal probabilities. And therefore, if you're finding 3 paths lead to one head only, then it's three of those, which is 3/8. Okay, back to 2 heads. Hopefully for that one you got 3/8 also. There are 3 paths here that have 2 heads in them. I see one here, and there must be another one. I missed it. One there, and one here. Okay, and finally at least one tail. Okay, at least one tail is 7 out of 8. At least one tail again means one tail or more. Basically that means the easy way to look at that is, well, which path does not have at least one tail? Only this top one, head, head, head. That's the only one that has no tail. So 1 out of 8 does not meet this criteria. So 7 out of 8 do. Okay, let's leave with this problem. So now we have a biased coin, a coin that's weighted wrong, or it's a trick coin, but the probabilities are different. Look, heads is more likely than tails. Your job is to figure out the probability of it getting exactly 2 heads. So what is the probability of getting 2 heads? Try it now. Okay, a little bit tougher, a little bit more work to consider, but one of the paths that leads to 2 heads is this one, head, head, tail. And another path that leads to 2 heads is this one, head, tail, head. And another one of the 2 heads paths is tail, head, head. Those are the 3 paths that lead to at least 2 heads, exactly 2 heads. And the probability of each one is determined by multiplying the probabilities along it. So 2/3 times 2/3 times 1/3. And then, but you'll notice if you follow all 3 paths, they have a different order of fractions, but all the results are the same. So basically, you have that same path 3 times, and your probability is this. That one's a little tougher. So again, same path 3 times. Okay, don't stop there. Please do the practice.